Alrighty, before we do lightning talks, we have a survey giveaway to do. So, the lucky winner of an iPad mini sponsored by iXReach is Majdi Abbas. Are you in the room? There you are. Congratulations. All right, you don't need to come up here. We'll get it to you after the session, but congratulations. All right, moving on up. First up for our lightning talks, we have David Meyer talking about OpenDaylight. Dave Meyer, are you here?
Okay, thanks. This is about OpenDaylight, something I somehow got myself involved in. I don't know how. This is my agenda. I'll give you a little bit of an intro into it, what the architecture of this is supposed to be, and how you might get involved. So what is it? It's an open source project. It's being housed by the Linux Foundation. By the way, if anybody's ever worked with those folks, they're very world class. They're really good. It's an open source project, and it has the goal of furthering the adoption and evolution of SDN. And the idea here is that we'll build a common industry-supported platform that will help this. It has this tiered membership model, so you could be a platinum, gold, or silver. The platinum members were the ones that kind of booted this thing up. This is Cisco, Brocade, Juniper, Ericsson, Citrix, IBM, and Red Hat, Microsoft, and Red Hat. What are the goals of this thing? As I said, it's to create a sort of a open source code base that people can use to build product and other things on top of, and kind of to boot up a open source SDN ecosystem. And we also want to have a broad industry kind of acceptance around this. And I think, one of the things is, we would like to see this as a basis for product as well. And then, of course, like any open source project or community, you want to have a great developer and technical community around it, and it really can't survive without that. And that's really true for any open source project. And in fact, there's a OpenDaylight Hackfest tomorrow and Friday in San Jose, where there'll be about 100 people involved in that sort of a community building activity there. And then when I came into this, and there were questions about whether or not it was going to be open and transparent and all of this kind of stuff because of the founders and all of this other kind of stuff. And I just said, look, I got elected board chair of the TSC, the Technical Steering Committee, and I just said, hey, look, all of this stuff's going to be open. So kind of uniquely, the TSC calls are open to everyone. They're recorded. The minutes are posted publicly. So there's a WebEx. You can just get on it and you can listen, or you can even talk. So it's unlike, say, the Open Networking Foundation or even the IETF, where the IESG has closed meetings. Everything's open. See, what's the code thing here? All of the founding members have contributed some piece of intellectual property in the form of code. So the Cisco folks they contributed a controller. IBM has things like Dove. NEC has a virtual network tenant application, things like that. But the reality is it's an open source project. So while these people booted it up, anybody can develop code, contribute code as an individual. And hopefully this will form a robust framework, and there'll be new applications and tools that sit on top of this, because I think, as most of us think anyway, that the real action in all of this SDN stuff is going to be in applications, not in the infrastructure. It's kind of mundane in a way. It's built under the EPL, the Eclipse public license, which is sort of something that vendors like, because they can bundle up their own proprietary pieces of this in their products. So, and I'll show you this in a second when we look at the architecture. So here's a picture of what it is. So the controller platform in the middle is sort of the key piece of this. And the idea behind it is that it has a few architectural features that are important. One is that the interface is going south from it, so it's listed there are things like OpenFlow and things like I2RS, and there can be other things like NetConf and the like. But there can also be proprietary things like Cisco has 1PK, GNOS SDK, things like that. And it's all pluggable, right? So for example, you could build a proprietary southbound because you had some SDK, and you could bundle it up if you wanted to. So that's one of the interesting features of it. Another interesting feature of it is this service abstraction layer. Now this thing is, the idea here is that applications that run on top of this thing shouldn't have to know what kind of southbound the application is talking to. It shouldn't have to know that. So the idea here is that you'd build an abstraction that would allow you to kind of not only take advantage of the unique features of the southbound, but also allow you to sort of do this in a model-driven way, so you wouldn't have to have, an API suite per southbound. And then the same thing on the northbound side, pluggable, model-driven northbound APIs. So that's kind of the idea behind it. A lot of these pieces are around right now, and a lot of this Hackfest activity tomorrow will be around the controller piece of it. If you want to play, wiki.opendaylight.org has tons and tons of information about what's there, what's planned, what architectural features there are, how to get code, how to build it, how to run it. So wiki.opendaylight.org. Mailing lists are all open. And in particular, the one on the bottom, the TSC, is Technical Steering Committee mailing list. That's where we do all our activity, and that's open. So if you want to see what's going on the TSC, just subscribe. They're all open. Let me just talk about governance for a second. Again, when this got booted up, this governance thing was very, very contentious. And I just put a pointer to the bylaws, which are just standard open source bylaws. The consortium has a board of directors, just like any other open source project that deals with business, basically, and hard decisions. It's initially comprised of the platinum members plus one of the gold and one of the silver. It's kind of standard thing. This is one of the things that's really nice about having the Linux Foundation. They've done this 100 times. They know how to do it. Then there's a technical steering committee. And basically, this is where the technical decisions get made if they need to be. And it's also where release trains and those things get defined. Now, in a regular open source or in a mature open source project, what you'd really want to have is the technical steering committee be comprised of the technical people from the main projects. But since we had to boot the thing, it's currently comprised of members that have been assigned by the platinum members. So I became the chair of the technical steering committee, but I don't expect that after a year or so, or however long my term is, that I would still be that, because, again, as I said, the well-functioning technical steering committee will have lead developers from the core projects. Let's see what else. Oh yeah, and of course, we talk about this thing in terms of membership and all of that, but it's open to anybody. It's open source project, so anyone can develop and contribute code. Anybody can get code. Anybody can get elected to the TSC. Anybody can get elected to the board, and anyone can help steer a project in any number of ways, just like in any other open source project. Since I'm the chair of the TSC, I just thought I'd talk about that just a little more. What we do is we set the technical direction and code train releases. And as I mentioned, the membership is kind of bootstrapped by the appointees from the platinum members. But the important thing is that the meetings, the mailing lists, and the calls are all open to anybody who wants to listen. So if you get on wiki.opendaylight.org and go down to where it says TSC, you can see the agenda and the call information. And the minutes are also there. And then there's also a technical workstream call, which is a technical call where we handle technical issues, and that's currently on, I think it's on Mondays, but there's the URL for it. And that's it.
Okay, any questions?
The architecture diagram? Which one? Oh, sorry.
Randy Bush, IAJ. How much of those are colored in already?
Okay, that's a really great question. So the middle controller box is, and a lot of the pieces of it. For southbounds, right now, there's an OpenFlow. There are two different OpenFlow 1.0 southbounds. There's some work going on sort of a proto I2RS thing. There's a netconf one. Northbound, there exists a couple of different proposals for what the model-driven approach to the northbound was. See, the main reason that it's all model-driven is because who knows what this stuff is going to look like. I'd rather be able to hand it a Yang model and then generate that, right?
We've historically been so good at network models.
Yang,
CIM, I mean, we could come up with a long list of failed ones.
yeah.
Yeah.
Well taken.
And OpenStack, had the bootstrap start of being handed a lot of code by NASA.
Yeah.
And so I'm
Rackspace.
just kind of wondering how much of this is real already.
There's a lot of code. There's a lot. But I don't want to leave you with the impression that there's anything like a completely ready-to-go working system. It's more like, here's a developer system, and we're going to start working on this. So there's a lot of code available, but not in production or consumable state by anybody but developers right now.
Okay, Dave, thanks very much. Alrighty, next up we have Randy Bush speaking on the suitability of ping to measure latency.
So now you get the traditional Comic Sans and the clicker is, Dave, did you just walk off with the clicker?
It's on top of the, oh, here it is. See where it is? Yeah.
Thank you.
I mean, it's cool and everything.
So, this is research. I guess this blinking right arrow is this. So, we were using the Atlas probe system to do some experiments, and we found a very high variance in ping times. In other words, we'd ping something, and it'd be 100 milliseconds, but the variance in that 100 milliseconds would be unexpectedly high. So we started to wonder, what's the actual distribution? Could there be a rich distribution? In other words, hey, lots of variance in the ping times and not flat. So we decided maybe before using these tools, we better calibrate them. I know that's radical, but there's some cute thing called Paris traceroute, which uses flow ID to explore through hashing, through forcing the hashes on the routers to force it to explore ECMP or lagged alternate paths. And what I mean by flow ID is, and it's the dark stuff up there. I wonder what this, yes, sorry about that. So these dark things control the hash that the router is going to use. This is UDP ping, this is ICMP, and the port unreachable response. So we could change those and cause the router to choose the alternate paths it had for ECMP and for lag. So we ran these, if you'll remember, I asked on Nanog for some help. We ran experiments. An experiment would take 8-10 hours, do hundreds of pings, just over to one destination, but across all these to get a fairly high reliable number. This is what it looks like. Here's Roma Tre University in Rome to Ashburn. And Linux, it's wonderful. Linux rounds the ping result. It believes that ping cannot have any resolution better than 3 digits. So you will see the red do this, but these curves are the actual ping results, and you'll notice a distribution of these curves. So a single ping, while altering the flow, had significant variance. Not big variance, but significant in this case. And so we went to explore why, and this is what we found. It was ECMP, a global provider, getting across the Atlantic with many paths. When you take those and you multiply them, you get a lot of alternatives. And it looks really ugly if you're trying to do science across this. Okay? So we then said, let's simplify things down. Let's get it down to something we can actually get some feel for. So we have a host in Dallas, and it's connected to a router that's connected to a router. This is a 9 times 10 gig path, lagged. Okay, we know the configurations and circuits and details on all these routers, and then there's one in Ashburn. Okay, so we ran the, source ID variant ping between these just over this path. The result is the worst case we found. The variance is very high. The minimal ping time was 32, 33 milliseconds. The maximal was 46. That says the variance is over 50% of the min. Okay? And these are clear bands. Now, what you've got in the red and the black going up there is the red is what you got. This is the CDF if you actually ran ping. That's CDF of measured ping. The black is if we assumed all these alternate paths had equal probability. What would you get? And notice it looks very similar. Okay, and the difference is, of course, it doesn't distribute over the equal probability. But something is really kinky here. Something is really kinky. What this calls into question, aside from you're going to have fun in operations, is there's a whole lot of research based on using ping to measure latency. Bye-bye. Okay, so we don't have a magic answer, don't hope. We're still digging, except I'm traveling. Some of the digs we did, it's not the host. We measured across here, looks dull and normal. Okay, so it's not the hosts, it's not the simple routers, etc. It's that path. Okay, it is very reproducible. The circuit loading was less than 50% aggregate. We do not know that the loading on a single circuit in the lag was not really bad. And that's because we've not been able, and this is where the router vendor help, to be able to actually find and monitor the queue lengths on the different circuits in the lags. Boo hiss. Different times a day, same thing. Different probe timing and spacing, same thing. UDP or ICMP, same things. MPLS seems not to influence things. Okay? The biggest thing we could find that influenced things is you can actually say how deep into the packet the hashing looks. And if you look beyond layer 3, in other words, into the port, those measurements we had where it was configured to go for the port were significantly worse. Okay? Here's a layer 3 only hash. This is a European transatlantic. Oops, that was a mistake. And so you'll notice it's fairly clumped. Fairly clumped. This is a different provider, different routers, et cetera. Sorry. Okay? This is, by the way, what happens when you say, oh no, it's something happened during the run. This is what something happened during a run looks like. You have that, you have your measurements, the event happens, everything shifted to the right, and then the world continues. So the funnies we were looking at were not event happens during a run. Okay, here's a summary of some different things we tried, Rome to Ashburn, Rome to Brussels, Rome to London, et cetera, et cetera. The dispersion of the variance itself varies, but I mean, that's that worst case. But there are significant ones. 5% and 4% are ugly when you look at it from a researcher point of view. Ops, they may not make that much difference. Okay? And we'd like a large number of measurements. But the Atlas probe itself is A, imprecise, B, there are 93 generations of them, all different, and C, the deeper we look into the Atlas probes, the more bugs we're finding. in those measurements that we used an Atlas probe for that caused us to get to this study, we chopped off some ugly data at the top that we couldn't figure out. We went back and looked. We were having some delays. In other words, we sent that packet out, and the Atlas probe claimed we got it back 2.5 minutes later. I kind of don't believe that. Okay? So I think there's little buggy poos hiding there in Amsterdam. Okie doke. And that's the story. So when it comes to measuring latency, you may want to do a little more than a simple ping, because what you get back from that ping is min, max, and mean, but you don't know the dispersion. The max could have been one packet, or all of them are up there at the max. Todd, you're heading for a mic. No? Ah, come on, somebody head for a mic. You're a boring audience. I won't invite you to speak next time.
Thanks, Randy.
Sure.
I'm going to want that. Thank you. All right, could I have Todd Underwood and John Van Appen up here, please? Come on, Todd, you're big. You can move faster than that.
All right, this is a tragedy. There's no coffee out there, so this talk is going to totally suck. Let me just tell you right now. But there's no point in leaving, because you know what? There's no coffee out there. So John and I were talking about this yesterday, and we just decided to slap this together. There's some big problems to be solved here, and we thought reviewing it quickly would give us all a sense of where some really interesting, challenging work is to be done. This is going to be a little bit different than some of the stuff you've looked at. Yay! All right, so let me introduce the problem. Shit's too slow. Like, stuff's slow. And it's slow in particular in the history of the web. There's these data. It used to be back in 2001, there was this very famous day. 8 seconds. People give up paying attention after 8 seconds. More recently, the adage is 4 seconds, and Google's got some evidence that most of us stop paying attention after between 900 and 1,000 milliseconds. We're like, no, I don't know, I'm just done. Right? You guys already stopped paying attention to me before I even started talking, so this is like fantastic, right? Users get distracted and leave. We are network engineers, so we spend all our time optimizing the network. But we started looking at it, it's like, is the network really the problem? Is that, like, we're just pounding this network hammer. So we wanted to review what's really contributing to end user latency, stack rank them, and look at solving the most serious of the problems. You gotta go back now.
Sorry, you already hit. Okay, anyway, the real contributions to latency, some of this came out in our discussion with ourselves, as well as I've done some testing for our residential network and was just terrified at some of the CPEs that our users had been trying to use on our 100 gig service at home. So obviously you have network design, that's what we all talk about all the time in our discussions. Can we route this better on the backbone? What can be done? The CPE thing though, that's pretty big. Last mile networks tend to be, well, ugly a lot of the time in the routing. And bad geolocation, you know, that happens. Then, of course, you see the websites that, wow, this is local if I do a trace route, but it still took 3 seconds to serve. That's odd. People doing it on poor quality servers, things like that. And then, of course, the fiber propagation delay. And that comes right into our last one, which is C. We'll talk about that later. There are some novel concepts to reducing network and delay in the network itself. This is a map of some microwave networks that have been built between Chicago and New York for high-speed trading, because the propagation delay of radio frequency energy in the air is a lot lower than light in fiber. So they gain about 25% or so, which is quite interesting. But this is where you come around to money can solve lots of problems, except C at the moment, but you can get closer to C at low bandwidth if you're willing to spend the money. You know, we were also discussing some math on this one, and Hibernia announced a few years back that they were building this new, shorter route between London and New York, and you know, we just decided to divide the latency into the cost of the route and realized that it was $80 million per millisecond that was saved across the Atlantic, and well, is that worth it? I mean, is there some other problem we can fix? Maybe for high-speed trading it's worth it, that seems to be what they think, but you know, for user performance, probably not worth it. Are there any more things we can fix? Well, the big solution here, CPE, we've got one, that's one big problem. Interleaving error correction, I was sitting here talking to one of our other engineers who's here, and his DSL line, which is connected to a large eyeball network to whom we connect locally in the market, is 80 milliseconds to our 10 gig port, sometimes 40 milliseconds most of the time, round trip, and it's a 40 meg connection. So people are clearly doing a lot of interleaving error correction on these lines. Is that really necessary? Are they that bad? Well, can we do something about that in the CPE? Buffering, well, I was doing some testing. I have a gig wireless router that one of our end users had us test out for them, and I was trying it on a connection to our network. I'm noticing the LAN-to-WAN latency in my testing is about 15 milliseconds. That's probably not so good. We all know this is bad. What can we do about it? Well, roll out better CPE. Can we get people to roll out CPE that works? Hey, we can fix V6 at the same time. I don't know if that's going to happen, but I think that's one of the things that's becoming more important, at least in the end user space. If you have your own eyeballs, tell them, upgrade the routers, upgrade the CPE, provide better ones in the first place.
Stepping through some of the additional problems, you can fix bad geolocation. We're not going to do that. Look, geolocation is really hard. It's messy. Some people do it well. Some people don't. It mostly works most of the time. It'd be awesome if it all worked perfectly all the time. This is not that big of a problem. We wrote it off. Not fixing this one. Geolocation's hard. Let's go shopping. Okay. So we can fix these web technologies. Your web 2. whatever site kind of sucks. It's badly implemented. People didn't take it seriously. So the solution is don't do that. Related solution, buy a bunch of RAM. Further related solution, don't use RAM as a capacity cache. I'll explain that to people who haven't thought about cold starting their application at some other time. A related solution, don't use leaky or bad virtual machines. Ruby is a fine language. It's actually not a fine language, but let's pretend it's a fine language. Don't use the Ruby VM. It's terrible. Run JRuby. Anyway, moving on. The real moral here is that many people treat web application as the thing you do after you're done building everything else, and they hire the stupidest, least experienced people to do that, and they don't think about it, and then they throw thousands of milliseconds of end-user latency. So don't do that. There's some big opportunities there, and we thought that was awesome. Aha.
Okay, and then, of course, I started nerding out on this when we were talking about the fiber side, and I'm like, oh, what's the standard index of refraction on this fiber? Can we do something about this? And then, well, I found this paper that's referenced here at the bottom, but, there are these people that have been making fiber that has a vacuum in the core, and the loss is currently pretty terrible, but the propagation speed is like 98% of the speed of light in a vacuum, which really is that would be an index of refraction of just over 1. And that makes a big difference. But, really, how much can we do in optimizing the typical fiber types? Well, I was sitting there with that New York to London thing as my thought. SMF28 is about 1.468 index of refraction. Using 300,000 kilometers a second as the speed of light. Yeah, 54 milliseconds if you multiply that in. If we get that a little bit better, we don't make that much of a difference. We can knock a few milliseconds off here and there. Is there something we can actually do? Meh. Maybe. Some types of fiber get you a little bit better, but most don't make much difference without other problems like putting a vacuum in the fiber and having loss that's completely ridiculous, 3 or 4 dB per kilometer. Where does this get us? What are the things we can do? Well, we're starting with long end-user delays. First, fix networks. Well, that's not that much. Fix CPEs. Hey, that's even more. Fix geolocation. I don't know if we're going to actually fix that. Fix web apps. Ooh, that's definitely the biggest. Improve propagation delay. Well, we can get a little bit better. Not much, maybe. Ending, get some user delay improvements, but can we do even better than this?
Okay, so here's the part where we say, we just haven't been thinking big enough. So if you look at the end user latency, it's the client latency, the network latency, which we can decompose into specific edge latency because that has particular characteristics, and the rest of the network latency and some server latency. The client latency you can't do much about other than ask people to buy better computers. You can do a little bit with how you deploy your web app. And the server latency we think is a big opportunity, but there's this network latency, and we're spending time doing relatively expensive, fairly fiddly things like optimizing paths and doing traffic engineering. I mean, Raz gave this long presentation about, oh, we're going to pick good paths, and sometimes they'll have less good latency, but we'll be able to handle all the traffic. It was really complicated. So that's fine. But the latency is bounded by the factor of propagation delay inside of glass and the speed of light, c. So we looked at fixing the propagation delay. what we think is the big opportunity here is people really haven't been looking a lot at increasing C. And when you look at the math, I think that the math, I mean, like, look, this is a time, lightning talks are speculative work. This is a time for big ideas, not the time to be timid. Like, the math is, once you fix the dumb web applications, you fix a little bit of the edge. Your next big opportunity is to fix C. So this other stuff matters, but let me point this out, that if we fix C, it actually changes everything about how we build networks. Everything about the internet changes. So what changes? Right now we build things out based on cost, and cost is usually a factor of a combination of space and power cost. We heard a lot about that at the data center gathering. Staff cost to a certain extent. Connectivity, where can we get the right kinds of good connectivity? The location is often based on end user latency, and end user latency is dominated by C. Like, all this other stuff into the wash. We've got some geopolitical factors, like don't put your data centers in places that have ridiculous taxes or like are going to be confiscated by, you know, bad governments or whatever. But like, if we can remove location as a constraint for where we build data centers, you know, we don't have time left in the lightning talk. We're running out of time, but I'm encouraging the audience. There's no one that I know of that's spending significant amount of time and money working on this, and I think it's, I mean, I don't think it overstates it to say this is the biggest opportunity that is presented to our community. This is the biggest horizon available for the internet today. Let's increase C. Thank you very much. I think we have time for a question if anybody is foolish enough. Oh, Majdi.
As an alternative to increasing C, have you considered developing time travel?
I believe A equals B.
I can't comment on unreleased products. I don't know if you have anything to say.
That would work also. I mean, really.
Instead of increasing C, can we just use D?
It has some poor handling of data structure. Oh, wait. No, sorry. Go ahead. Chris.
Hey, so the approach we were taking at Comcast was we were considering doing superconductivity in the cable plant. You're talking about the last mile delays. The way we were looking at that just to speed up the electrons.
Yeah.
I guess it's kind of a similar kind of idea the way you were going, but we were investing in liquid nitrogen, not speeding up time.
I feel like all the solutions here are speeding up time, liquid nitrogen, or vacuums. I mean, all those things sound great.
Well, there's, I will point out that like depending on how well we can develop, like what rate at which we can propagate entangled particles, there are some non-speeding up time approaches to this. There's early work that I'm not really prepared to publicize related to that, but anyway, if you can distribute a large number of entangled particles, there's some evidence that you may be able to instantaneously or super instantaneously transmit information. And I do have a business methods patent on the phrase super instantaneously, by the way, so please see me if you'd like to use that. Brandon.
It's similar to the previous comments. I'm also disappointed you didn't explore the possibility of all of us just moving closer back together and recreating Pangea.
Well, you know, we did have this discussion about, you know, boring through the center of the Earth to shorten the fiber path, and we decided that was a minor optimization compared to just putting it on the bottom of the ocean.
Joe Provo, ITA Software by Google. Todd, you started to leak some of the information about the research we're doing on packet entanglement theory. I'm a little upset, but you may not have been aware that I've been working on the grand unification of packet entanglement theory with your probabilistic addressing methodologies from a previous NANOG. So we can have a truly, truly quantum internet.
Okay, that's fantastic to know, Joe. I didn't mean to step on any unannounced work. It may be that these ideas are so obvious to so many people that there's a lot of different people approaching it, and that's fantastic. Great. Any other questions? Thank you all. Think bigger, C.